In this video, we're going to have a look at some literature on LLMs. So let's start with the following questions, right? So what if a model could learn a new task from just a few examples? In this review, we're going to focus in LLMs. We're going to explore their capabilities and limitations. There's 3 papers that I found super interesting. The first one is language models are few-shot learners. We have scaling laws for neural and language models, and we have long-form factuality in large language models. The first 2 are from 2020. They are foundational. And then I found this one from 2024 that I thought was very cool. And before diving into the insights, it's important to understand the foundational concepts of how models like GPT-3, which is the basis for a lot of the research literature that's still out there. And at least, I'm doing this in 2024. And unlike traditional models, the GPT-3 can perform tasks based on a few examples during inference without updating its parameters. So let's explore the key methods. So we have zero-shot learning. So the model is given only a task description and must predict the answer without seeing any examples. For instance, you could ask GPT-3 to translate cheese into French without providing any prior translations and relying purely on its internal knowledge. Then we have one-shot learning. In this setting, the model is shown a single example alongside the task description. For example, after providing one translation, like sea otter leads to loutre de mer, GPT-3 can use that information to infer the task and translate cheese. This one example helps the model understand the task better. And then we have few-shot learning. So the model is provided with a few examples to enhance its understanding of the task. If given translations for sea otter, peppermint, and plush giraffe, the model can better infer how to translate cheese based on the patterns it observes in the examples. And these in-context learning approaches, they are a departure from the traditional fine-tuning, where the model's parameters are updated after being exposed to numerous training examples. In fine-tuning, the model is adjusted iteratively through a series of gradient updates to improve its task-specific performance. For example, the model could be trained on translations such as sea otter leads to loutre de mer, and then peppermint leads to menthe poivrée, updating its parameters after each example until it can reliably translate cheese and other words. Now, what is important to have in mind, right? So I also want to share, this is extremely expensive in general. So fine-tuning is so much more expensive. And this is why few-shot learning, and this is, from 2020, this was groundbreaking because it was understood that a model like GPT-3, and, of course, now this is legacy, you didn't really need to fine-tune it for these tasks, right? You could just give it a few examples and the performance would explode. And now this is exactly what I want to show to you. So the question that I would ask, so how can a language model perform tasks it wasn't explicitly trained for? And in the paper, and this was the goal of it, so a model with 175 billion parameters, so this massive scales enables it to perform few-shot learning, where the model learns to perform tasks from just a few examples provided in the prompt. And this was the key insight, few-shot learning. This was actually something that this paper introduced. So they were the first to say, this is a topic that exists. So imagine showing the model a couple of examples of English sentences related into French without any prior training on translation tasks, and they can infer. So the model's ability to generalize from minimal examples reduces the need for large task-specific datasets and fine-tuning. And this flexibility opens doors to a wide array of applications using a single general-purpose model. And this was how they did it, right? So let's cover this. So we have the accuracy of zero-shot, one-shot, and few-shot. And very similar to what we have seen, the model does improve with the number of parameters. So 175 billion would be here, the GPT-3. But the thing is that it not just improves a little bit, it improves a lot. And even if you just give it one, right? So if you just give one example, it's already so much better. And then, of course, there's a marginal improvement over time, but it does further improve. Have in mind that there's a limitation here, but if you give it 3 or 4, your performance further improves. Therefore, if you want your prompts to have better outcomes, give it at least one example. And now if we address here some limitations here, so GPT-3 has its pitfalls. So the model can exhibit racial biases, particularly in sentiment analysis tasks. So GPT-3 tends to assign more positive sentiments to a certain racial terms over others, reflecting biases present in the training data. As I think I've shown to you, LLMs are not random. They're very biased. And the thing is that we need to recognize that these biases exist, because this is crucial, right? So if we don't understand that these biases exist, then we're not really fully using it. So have in mind that if we are describing specific ethnical people, right? So if you have, like, for instance, here, Asian, Black, White, Latino or Latina, Indian, Middle Eastern, we have here different sentiment score provided by the GPT-3. And for instance, Black has a generally lower sentiment score. Of course, it approximates with GPT-3, but still, right? If you look at, so this will be White, Black, and Middle Eastern, the sentiment score of how the models describe is lower versus Latino, Indian, and Asian. And this is very important for you to have in mind, right? So if in your prompt you describe or you include characters that would be referenced by any of these ethnical populations, you may have different words that represent different sentiments. Now, let's cover the second one, scaling laws for neural language models, how to optimize performance. The question was, does increasing a model size always leads to better performance? And Kaplan had a look at it, or Kaplan and his team, and they discovered that power law relationships governing the improvement of loss with respect to model size, dataset size, and computation. So the researchers found that increasing compute dataset size, and model parameters lead to steady, predictable improvements in the test loss, and with performance following a near linear power law trend. These findings suggest that growth in these areas continues to yield benefits without immediately reaching plateau. Have in mind that, again, this was 2020, right? So currently we now have far more tokens. I did not find a good paper that was actually updating all of these findings, but this was the finding at the time, right? So this was still very, very linear. Now let's have a look at each of them. So the left graph demonstrates a steady reduction in the test loss as compute increases. Same thing for the middle one, but this one is connected to dataset size. And then the right graph as related to the parameters also leads to higher performance. And as a general conclusion, so the graphs show that scaling any of these resources leads to consistent performance gains, suggesting that there's still room to improve models by increasing these factors. However, the cost in terms of compute and resources might still need to be balanced, because it does get much more expensive, right? Because you're there, increase everything. This is very, very expensive, and this is why this is a $1 billion industry that requires $1 billion expenditures. Now, let's look at the third one, long-form factuality in large language models. And the thing was surpassing human accuracy. So this was exciting. Question was, Can large language models ensure factual accuracy in long-form context, even more so than humans? And in the paper, Jerry Wei, their team, they explored this question by evaluating the factual accuracy of LLMs when tasked with generating long-form content in response to fact-seeking prompts. And the study addresses the growing concern that while LLMs are powerful in language generation, they sometimes introduce factual errors. So this would be called the hallucinations. And this is especially true, or this is especially concerning when you're dealing with open-ended topics. So the key insight for this paper was LLMs can surpass human evaluators with SAFE. And what is SAFE? So this is what the study introduced. So SAFE is self-attention, fine-tuning, and evaluation. This is a method designed to help LLMs verify the factual accuracy of the content they generate. And remarkably, when SAFE was applied, the model outperformed human evaluators in verifying factual accuracy. Therefore, SAFE annotations were correct 76% of the time in case where human evaluators disagreed, providing that with the right assistance, LLMs can be more reliable than human annotators in verifying long-form facts, all while being 20 times cheaper than humans, right? So it's better and cheaper, which is always, is it really like that? But this is how, or this is what they have shown here. This is a game changer when your applications require high factual precision at scale. So for instance, a lot of the things that I do, they require that they're very, very factual. Therefore, this is actually very, very cool for me. Now, another thing that this study went and explored was, okay, what if we compare the different larger LLMs? And this is a takeaway that, yeah, larger LLMs are more factual. So there was a strong relationship between model size and factuality. So larger LLMs, and in this case, they had GPT-4 Turbo, Gemini Ultra. They showed an improvement in generating accurate long-form content. So they compared their accuracy metrics. So this would be the F1 scores. Not going to cover what is an F1 score, but the bottom line is that it represents a measure for accuracy in imbalanced data sets. But that's as far as I'm going to go. Bottom line is more or bigger F1, the better the model. And this was the outcome. So they looked at it. So they look at each of them, and you see that bigger models, they had a higher F1. So GPT-4 Turbo, Gemini Ultra, they are bigger models. And therefore, this is what you can try to rely on, right? So if you go to a more recent model, which would likely be a bigger model, you're also most likely to get more factual outcomes. And if you're curious about this F1 at 64, F1 at 178, so the data set that this was evaluated on, there were multiple facts. And for those where the median number of facts was 64, this was the outcome, right? So 64 facts. We had 95% F1 from the GPT-4 Turbo. When we had 178 facts, it was still a GPT-4 Turbo, but have in mind that if we have a lot of facts, our accuracy decreases significantly. So this is another insight. Therefore, if you want to be sure that your model is being as accurate as it can be, rely on simpler tasks. This was another outcome here. And then, as a general conclusion, so this study emphasizes that while LLMs are not flawless, they are steadily improving in their ability to generate factually accurate long-form content. So this is the technique called SAFE. I have not been able to see how it can be applied yet, because at the time of this writing, this is still new. But hopefully, there will be a time where I actually show it to you. So I'm excited about that. And LLMs are not only closing the gap with human evaluators, but they're actually surpassing it with some of the new techniques. So this is an exciting thing. Now, final question to you. What does the future hold for large language models? And if you found this interesting, now if you find these papers interesting and if you know of some, share them with me. I'm also here to learn, and I would love to do another video on LLMs. Now to you, if you find research papers interesting, and if I have not covered them, share them with me. I'm also here to learn. Till the next video, have fun.